David's talk today is the physics of atmospheric instability, lightning, and global warming. Let's welcome David.
Thank you. It's a great pleasure to be here. I have to say that when I switched from physics to atmospheric science, I asked a lot of stupid questions. And one of those questions is actually the centerpiece of this talk. And that is, what sets the speed of rising clouds? And it turns out this actually wasn't that stupid of a question. At the time that I asked it, there was no theory for cloud speeds. And in fact, even today, there's no theory for cloud speeds. We can measure those speeds, but if we don't have a theory for them, then we can't say how that important aspect of the atmosphere is going to change, say, in the future. So what I'm going to talk about is progress on related topics in the atmosphere. And all of these topics are related to each other in a variety of ways and related to this question of what sets those speeds. And each one of these arrows on here indicates one of those interconnections and also is a part of this talk. So as we go along, we're going to add little nuggets of insight to this diagram. Now, before 2013, let me tell you what the state of affairs was on these various aspects of the atmosphere. Regarding humidity of the atmosphere, we had no theory, especially for the convecting tropics. Regarding the instability of the atmosphere, and I'll describe what that is in a little bit, we had no theory. Regarding drag on rising clouds, we had no theory, and actually very little understanding at all. The debate wasn't about exactly how much drag there is or which processes are responsible for the drag. The question was, is there any drag at all? And we had no good predictor for lightning. And as I mentioned, we had no theory for the speed of these rising clouds. Now, 2 years later, we've made some progress, and that's the progress I'll report on here. We have a theory for the humidity of the convecting troposphere. We have a theory for the instability of the atmosphere. We now know whether or not there is drag on rising clouds. We have a good predictor for lightning, which matters for a reason I'll talk about later. And I think we're getting close to a theory for the speeds of rising clouds. Getting back to that originally, kind of naive question. So let's begin with this arrow here. And this is the only arrow here that's really background material. The rest will all be research results. But I want to give a little bit of background, and really 5 minutes of background maybe, on how the atmosphere works and what I mean when I say atmospheric instability. So this is a good 0th order picture of the atmosphere. You have the sun bringing heat and energy down to the surface, and that evaporates water. Meanwhile, aloft in the atmosphere is cooling to space in infrared, so it's cooling by radiative emission. So you have heating down here, you have cooling aloft, and you need some mechanism to bring the heat from the surface up to the atmosphere. And that's the job that clouds fulfill. They scoop up that water vapor, and they condense it aloft where the radiative cooling is. So they provide latent heating to balance the radiative cooling. And an important fact here is that the air in the clear air, the non-cloudy air, is sinking. And the air in the clouds is rising. It's very binary in that way. And in fact, we can even simplify the problem further just by thinking about those two flows, the air rising in clouds and the air sinking in the environment. And we can be even more crude and represent the atmosphere with a two-stream approximation, where we assume that at a given height in clouds, all of the cloudy air has the same properties, and at a given height in the clear air, all of the clear air has the same properties. That allows us to, say, numerically discretize this system and solve it fairly straightforwardly, or even write down equations with pencil and paper. Now, if that's all there were, the atmosphere would be a very boring place. But there's something that happens that makes it interesting, and that's the exchange of mass through turbulence between the rising clouds and the sinking clear air. And we refer to this process by two words, entrainment and detrainment. Entrainment is the turbulent injection of clear air into the clouds as they're rising, and we denote the rates by this epsilon. And detrainment is the ejection of air from the clouds into the clear air as they're rising. We denote that rate by this delta. Now, what does entrainment do? Let's just think about this for a second. What entrainment does is it brings air into the clouds that is drier than the cloud itself. So the cloud is saturated, the clear air is subsaturated. So it's having a drying effect on the clouds. And we can see that in particular if we think about a parcel of cloudy air. So a parcel of cloudy air is saturated, it has, say, liquid water in it. And as that parcel is rising, it's going to lower pressure. There's just less overburden above it. So it's expanding and getting colder. And as it gets colder, the specific humidity has to decrease just by Clausius-Clapeyron. But there are really two ways in which that can happen. If that parcel of air is not entraining, then what happens is the water vapor condenses onto the liquid drops, and that then releases latent heat. And that latent heating keeps that parcel nice and warm and buoyant as it's rising through the atmosphere. On the other hand, if that cloudy parcel entrains a blob of dry air, then this parcel can reduce its specific humidity by simply diffusing water vapor down the water vapor gradient into that dry blob. And that process releases no latent heat at all. So you see that this parcel that entrained is colder and less buoyant than it would have been in the absence of entrainment. So entrainment makes cloud parcels or clouds colder and less buoyant. So now let's picture a world in which we have no entrainment. Or we could still have the atmosphere doing its thing, this state of what's called radiative convective equilibrium, where you got this balance between the radiative cooling aloft and the condensational heating from the clouds. And you would get a temperature profile that looks qualitatively like this. The temperature decreases with height. And basically the clouds in the environment would have very similar temperatures because they have a little bit of buoyancy as they rise, but it would look like this, fairly placid place. Now, when I was a kid and I tried to picture God creating the earth, I imagined a guy who was mostly benevolent, but on that particular day, just a little bit cranky. So imagine he's made the earth, he sees this radiative convective equilibrium, and he saw that it was good. But then he said, let there be turbulence. And the moment he does that, these clouds start entraining. And we know what entrainment does. It makes clouds colder and less buoyant. So now they can't rise up to this atmosphere. They're not warm enough to do that. So they're not providing that latent heating aloft. Meanwhile, there's still radiative cooling up there. So the upper part of the atmosphere is getting colder and colder. And the temperature profile starts to tilt over like this. And it tilts over and over and over until finally, even these entraining clouds have enough buoyancy to rise through the depth of the atmosphere. And you then reach a new radiative convective equilibrium, one between these entraining clouds and the radiative cooling. So in this situation, what we have are entraining clouds that are rising with a little bit of buoyancy, but basically with temperatures the same as the environment, and rising slowly with relatively small speeds. But now you can imagine what would happen if we got a big storm cloud. A big storm cloud can have a large superficial area to volume ratio, and that can insulate it from the effects of entrainment. So now this cloud can rise in a way that's relatively non-entraining, and it can follow that original temperature profile. But you can see that it's going to have a large buoyancy. The distance between those two curves at a given height is proportional to the buoyancy. That's the temperature difference between the cloud and its environment. And if that's the buoyancy, and buoyancy is a force, we can integrate that force up in the vertical to get a work or an energy, and we call that energy CAPE, convective available potential energy. CAPE is proportional to the area between those two temperature curves. And what it is the specific energy that's available to storms to do with as they wish, to convert it into their own kinetic energy, to perhaps dissipate against drag, to generate hail, lightning, whatever it may be. And it's really the existence of entrainment, the existence of this turbulent exchange, that makes CAPE be there in the first place. Because the atmosphere is pegged to that temperature profile that allows those commonplace entraining clouds to rise. But then when a non-entraining cloud can come along, it can go with gusto. Now, CAPE is a variable that's monitored very closely at weather centers all over the world, including at the Storm Prediction Center in Oklahoma, where by this picture you'd think they do nothing but stare at pictures of the US, but they do more than that. They issue, for example, these types of warnings. Now, when I made these slides, it was Thursday, this past Thursday, so I just pulled down the map of the severe weather outlook that they issued. And this is the forecast for Friday, the next day. And what you see is this kind of Y-shaped region here of severe warning here, and the lower half of Florida here as well. So you might wonder, what are the meteorologists looking at? What variable are they thinking about when they decide to issue these warnings, or at least, outlooks? They're not quite warnings, are they? But forecasts of potential severe weather. Well, let's look at the distribution of CAPE for Thursday. And this is what it looks like. I apologize, it's hard to tell the correspondence between this and the previous map because they're showing CAPE over the oceans, and the outlines of the US is kind of hard to see, but I'll outline it for you. There's that Y shape that, where we had the severe warning, severe weather potential, and then the lower part of Florida here, another high CAPE region. So CAPE is one of the most important, if not the most important variable in terms of being an ingredient for severe weather. And it's something that's used operationally to make forecasts of severe weather. Okay, so what have we learned? You've just now learned everything there is to know about the atmosphere. What's actually measured is the temperature structure, just like we saw in the cartoon picture. You send a balloon up with a thermometer on it, measure the temperature, and from that you can calculate CAPE. So we've learned that clouds rise, clear air sinks. We've learned that the atmosphere's temperature is set by the commonplace entraining cloud, but that then makes room for CAPE, this potential energy available to storm clouds, which, if they're not entraining, can take advantage of this instability. And it's an instability in the sense that if God were to snap his fingers and say, okay, turbulence off, the atmosphere would explode. All the clouds would take advantage of this energy. And the energy density in terms of joules per square meter would be comparable, same order of magnitude as a nuclear explosion. So that gives us a little background on instability of the atmosphere and we see how that would relate to speeds, because the clouds can convert that energy into kinetic energy. So let's just throw CAPE up here. That's just a little reminder for what we've learned about that. Now let's think about lightning and how lightning might relate to instability of the atmosphere. And you might ask, why would we bother studying lightning? And yes, some people get struck by lightning, but perhaps more importantly, lightning is responsible for triggering wildfire. And lightning's played that role through the history of evolution, has really shaped evolution through its generation of fire. And even today in the US, where we have lots of people running around, we have electricity, we have cars, we have cigarettes, half of the wildfires rather in the US today are caused by lightning. That's a fact. If you don't like facts and prefer anecdotes, we can simply look at a map. If you hadn't noticed, California is on fire in a variety of places. And there are currently 8 active fires, and 4 of those were triggered by lightning. 4 is half of 8. So there you go. Proved. So we want to be able to predict this lightning. We want to be able to predict it for a variety of reasons. Maybe for an operational reason. We want to make warnings as to lightning potential. Or maybe we want to look out into the future and say, okay, the climate is changing. We're going to continue changing it. How will lightning change? And then, therefore, how will wildfires change? Well, the state-of-the-art proxy or predictor for lightning dates back to 1992. And to explain it, I need to tell you, just define 2 variables. The first is F, which will be the lightning flash rate in a global climate model column. So global climate models are discretized, of course, and so there's a column of atmosphere. And so this F is the lightning flash rate in that column in terms of hertz. Now, already for me, little warning bells start going off. This is not per meter squared per second, it's per second and per grid column. So you change the size of your grid spacing and all hell breaks loose. Okay, but fine. Then we got H. H here is the height of the deepest convective cloud in the global climate model column. So those are the two variables. And the 1992 proxy uses H as the predictor here. And the equation is the following. The flash rate over land is proportional to the height of the deepest cloud to the exponent 4.90, which I think is an incredible number of significant digits. Now, there are a few problems with this proxy. One is that if the amount of deep convection doubles in the column, we know that that should double the amount of lightning. Lightning is made by thunderstorms. If I have twice as many thunderstorms, I should have twice as much lightning. But if they have the same height, that doesn't change the prediction from this proxy. So that's one problem. Another problem is that, well, this doesn't work over the oceans. So over the oceans, what do? Of course, we change the exponent to 1.73, naturally. And, well, okay, it's not all that satisfactory for a variety of reasons. And probably the most basic reason is that this has no connection to the physics involved in the problem. There's nothing about, you can't with pencil and paper derive 1.73. And another problem, of course, is that if you had a storm that moves from the ocean onto the land, the proxy would, predict some pretty ludicrous changes in the lightning flash rate. So let's see if we can do better. So our new hypothesis is really a combination of two separate hypotheses. And now I should say that the F we're going to use now is per meter squared per second, flash rate. So our first hypothesis is that the flash rate is proportional to the energy that's available for convection. It's available for making lightning. If you have no CAPE in the environment, you can't possibly make lightning. So it seems reasonable to guess that more CAPE means more lightning. But on the other hand, we can't have any storms or any lightning if there are no storms on. You can have all the CAPE in the world, but if there are no storms happening, you're not going to make lightning. So the other hypothesis would be that the flash rate is proportional to some measure of convective activity, and precipitation is as good as any measure of that. So we'd say the flash rate is also proportional to the precipitation rate. And that then gives us this very simple proxy, the flash rate being proportional to CAPE times precipitation. One benefit of this is that if the amount of deep convection doubles, the precipitation rate will double, and so the flash rate would double according to this proxy, so that's good. Another benefit is that this could potentially explain the difference in lightning flash rates over land and ocean. An explanation would have to do with the difference in thermal inertia of the ocean mixed layer versus the land surface, and taking into account the diurnal cycle. And it's also connected to at least some basic physics involved in the problem through an energy budget. Now, if we're going to advocate for a proxy like this, we have to demonstrate that it works. And to do that, we're going to need observational data for these three different things: the lightning flash rate, CAPE, and the precipitation rate. So for the lightning, we're going to use this amazing data set. It's called the National Lightning Detection Network database. And what it does is it records every lightning strike over the US, and it records exactly where and when it happened. It does that with a network of radio receivers around the US, all listening for the EM pulses emitted by these lightning strikes. And then by time of flight, they can pinpoint where that lightning strike took place. For CAPE, we're going to use a collection of these radio sondes that I mentioned before, which are these balloons basically with thermometers stuck to them. They're released from about 70 locations over the US twice a day. Unfortunately, that limits us to this doing this analysis once every 12 hours. The balloons are expensive, so they're not done all that frequently. One of the spots, by the way, is at the Oakland Airport. For precipitation, we'll use this very nice gridded data set put together by the NOAA River Forecast Centers, which unfortunately have only done this for the year 2011. So we're going to be restricted to the year 2011. Now we're going to do something very simple. We're going to take the CONUS mean flash rate, and we're going to scatter plot it against potential predictors. We're just going to see how they do. So for the first one, we'll scatter plot lightning flash rate, that's on the y-axis there, against precipitation on the x-axis. And we see that, well, you get an R-squared of 0.29, so precipitation explains 29% of the lightning flash rate variance. If we plot this against height of the deepest cloud to the fifth power, here I'm rounding 4.90 up, you get an R-squared of 0.39, so we're doing a little bit better. If we plot lightning against CAPE, we get an R-squared of 0.52. Now we're explaining a majority of the variance But when we combine these two and plot Cape lightning flash rate against Cape times precipitation, we get an R-squared of 0.77. So we're explaining 77% of the variance. Now, when I first saw this plot here, I was quite skeptical. I thought there's no way this could turn out this well. We've got 3 completely independent data sets, and in meteorology, things don't typically work out this well. So I thought this must be dominated by something simple or silly, like the diurnal cycle. So the next step, of course, was simply to plot the 2 time series and see how they compare. And that's what it looks like for the year of 2011, with Cape times precipitation being the blue curve and lightning flash rate being the red curve. And to our surprise, what you find is that these 2 things are really well correlated on timescales ranging from diurnal to the seasonal, and even on timescales in between, like the timescales of storms moving across the US. So this is what gave us confidence to then go ahead and apply this proxy in other ways. And I should say, when I gave this talk once, someone complained that they were having a hard time telling the difference between the blue and the red curves. But that is the point. Of course, they track each other really quite well. OK, so now that we've got this proxy that we have some faith in, we can now turn to global climate models. Global climate models do not predict lightning. It's just not one of the things that they do. But they do predict Cape, and they do predict precipitation, because those 2 things are just part and parcel of simulating the atmosphere. So we're going to look at 11 different global climate models from what's called the CMIP5 archive. We're going to look at a business as usual scenario and look out over this century to see what, if any, change in lightning we should expect using this proxy. And if we do see a change in lightning, which factor is responsible for it, Cape or precipitation? And here I have to acknowledge Jake Seeley, who's sitting somewhere in the audience. I see him being nudged. He really did a very nice work here. Among his many talents, he is a master of CMIP5 data. And this is a non-trivial thing to do, what I'm going to summarize on the next slide. So you take all these global climate models, run on a variety of supercomputers around the world, and we can boil numbers down to the following. For the continental US, we find that the change in flash rate per degree of global warming is 12%. And if we look at how that breaks down into changes in Cape and changes in precipitation, we see that the change in precipitation is small, about 1%. In fact, the models don't even disagree on the sign. It's such a small number. But the models are unanimous in saying Cape over the US is going to increase, and will increase dramatically with warming, 11% per Kelvin here. So it's increases in Cape that's driving an increase in this proxy for lightning. Now, if you look over the 21st century in a business as usual scenario, we're expecting to warm the planet by about 4 degrees. And so 12% per degree, that gives us about a 50% increase in lightning flash rate over the continental US. That's the average response from the climate models in the business as usual scenario. So what we've learned here is that we've got a new proxy for lightning, Cape times precipitation. It explains 77% of the variance in CONUS mean lightning flash time series. And if you apply this to global climate models, they're predicting an average of a 50% increase in lightning flash rate over the century due to global warming. And that increase is driven by increases in Cape, which is very interesting. OK, so let's put our little nugget of wisdom here. Flash rate is proportional to Cape times precipitation. But now that we've learned this fact, that flash rate is should increase, and that it should increase because of increases in Cape, that leads us to the question of, well, first of all, is this Cape increase realistic? This is not really something we can measure in today's world because we haven't had a long enough period of global warming to extract the signal reliably with our measurements. But could this just be a quirk of how the global climate models work? It turns out that Cape really does increase, and we know that from a different line of evidence, which is from cloud resolving models. So these are models where you put very few parameterizations into them. You put the governing equations for a fluid in, you put in radiation, you put in Clausius-Clapeyron for water, and a little bit of microphysics to determine how little condensed water particles glom together and fall out as precipitation. And you get it running here over the ocean, and it just bubbles up and starts making clouds quite naturally. So what you can do in a simulation like this is, for example, increase CO2 in the atmosphere. And this is what I did in 2011. This is the first global warming experiment in a cloud resolving model. And what was found is that CAPE increased by 7% per Kelvin, which is suspiciously similar to the Clausius-Clapeyron rate of increases in water vapor. And at the same year, a separate group at MIT did a similar experiment. They didn't increase CO2, but they simply increased the sea surface temperature in their cloud resolving model. Different model, different approach. They got 8% per Kelvin in terms of increases in CAPE. So we're fairly confident that CAPE will increase in the future and increase in this kind of large way, large dependence on temperature. So why then does CAPE increase? Well, CAPE is generated by the entrainment of dry environmental air. That's what makes the temperature curve colder than it would be for a non-entraining cloud. But why is the environment dry in the first place? Why isn't the environment just saturated? What's going on there? So we really need to know what sets the relative humidity of the atmosphere. Before we know that, we have very little hope of understanding how much CAPE we have in the atmosphere or how CAPE should change in the future. So we would like to answer this question, but instead we're going to have to back up and try to tackle this one. What sets the humidity of the atmosphere? And to answer this question, we can go back to our simple model of the atmosphere. This two-stream approximation of radiative convective equilibrium, where clouds go up, clear air goes down, and we can discretize all of those and assume homogeneity of properties at each level within the clouds and within the environment, retaining, of course, the turbulent exchange between those two streams. And when you go through the math, what you find is an equation like this. It says relative humidity is equal to convective moistening rate divided by the convective moistening rate plus the compressional drying rate. And we write this in terms of variables as follows. Or, as you may recall, though it was vast, delta is the detrainment rate variable. So we write relative humidity equals delta, the detrainment rate, which is moistening the environment, divided by delta plus gamma. And gamma here is the fractional water vapor lapse rate. QV star here. QV is the specific humidity, so the mass fraction of water. And we put a little star in it. That represents the saturation value. And gamma here is 1 over QV star, ddz of QV star, with a minus sign there. Z is height. That's right. So what is going on with this equation? How can we think about this? Instead of going through the actual derivation, I'll give a derivation that's a little more squishy, but helps us to see what's happening. So we've got clouds that are rising up. They're going up. And the clear air, the environment, is coming down past it. So they're sliding past each other. And as they go, the cloud is spitting out water vapor. It's spitting out air that's saturated with water vapor. And that delta, that detrainment rate, is a very important variable. 1 over delta, 1 over the detrainment rate, is a length scale. And the meaning of that length scale is the following. It's the length over which the environment adjusts towards the properties of the air being detrained by clouds as that clear air sinks. So the clear air is sinking, and as it goes a distance 1 over delta, it's substantially adjusting towards the properties of the air being ejected by the clouds. So if we think about water, what's happening is that the environment is adjusting towards saturation because the cloud is emitting saturated air. And it's adjusting towards saturation on a length scale of 1 over delta. So what that means is that the environment lags, its QV, its specific humidity, lags from the saturated QV star by that distance 1 over delta. So basically, QV here equals QV star a distance 1 over delta higher. And same thing here. QV equals QV star, distance 1 over delta higher, and so on and so forth. So if we zoom in on one of these, what we're interested in is relative humidity at a given height, of course. So relative humidity is this purple thing divided by this orange thing. It's QV, the actual specific humidity, divided by the saturation specific humidity. Well, from what we just learned, the QV down here is equal to the QV star, a distance 1 over delta higher, because the clouds are detraining saturated air into the atmosphere. And so we can write relative humidity as QV star up here divided by QV star down here, and write it like so. We can then Taylor expand, and this generates the gamma that ddz of QV star divided by QV star, multiply the numerator and denominator by delta, and we get the expression that we saw on the previous slide. So what's happening here to set relative humidity in the free troposphere is a competition between two processes. There's the convective moistening from the clouds detraining saturated air, and also the compressional drying of the air. If the clear air were left to its own devices, untouched by clouds, it would simply compress and compress as it goes down, moving to higher and higher pressures, and that would dry out the cloud because it increases QV star, it increases the saturation-specific humidity. And it's the balance between those two things that sets the actual relative humidity. So that allows us to put a little piece of insight here. And there are actually many more things that you can do with these equations that I don't have time to talk about, including explaining why the relative humidity profile in the atmosphere has the characteristic shape that it has, and also making predictions for how relative humidity changes as we warm the atmosphere, predictions that you can then validate using those cloud resolving simulations. But for our purposes, we're more interested in understanding what sets the instability of the atmosphere. So we want to get to this question. How does humidity affect the instability of the atmosphere? Well, first let me tell you the meteorological lore, which is quite hand-waving. It goes something like this. It says, well, you know, a cape has something to do with water. And so, in fact, more than that, you know, those big storms are using water vapor as basically their fuel. They're using that as fuel to power their way through the atmosphere and generate those large buoyancies. And so at cold temperatures, the atmosphere can hold less water vapor, and so there's just not that much fuel for storms. But as you warm the atmosphere can hold more water vapor, and you can get bigger and more powerful storms. So that's basically the level of the lore. And the implication of this, then, is that CAPE would increase exponentially, just like QV star as a function of temperature. So QV star exhibits Clausius-Clapeyron scaling increasing by about 7% per degree. And so if you buy this kind of explanation, then CAPE would also increase by about 7% per degree, which, as we saw from the cloud resolving simulations and from the climate models, you get an exponential increase like that. So that's just lore, though. That's what I just said. So CAPE would then exhibit the same kind of scaling as saturated specific humidity. But can we do any better? Can we move beyond this to a theory that's based on pencil and paper theory? Well, if we're going to do that, we're of course going to go back to this simple picture of the atmosphere, because it's something that's analytically tractable, as it turns out, where we assume this two-stream approximation, cloud air going up, clear air going down. And when you crunch the numbers, I'll show you what you get. So this is the meteorological lore, this important piece of information that we believe, without great theoretical justification, that CAPE increases like QV star. When we go and crunch the numbers and actually develop a theory, we get an expression that looks like this. So there are various things going on here. First of all, well, let me just go through the terms. You've got relative humidity. You have 1 minus the tropopause temperature, the temperature at the top of the atmosphere, divided by the surface temperature. You have a latent heat here, telling you how much sensible heating you get for condensing water vapor. And you have QV star, the saturated specific humidity. And if we step through these, it's interesting to note that we have an RH here, and not a 1 minus RH. And why would I think we should have a 1 minus RH here? Well, it was the drying effect of entrainment that generated CAPE. But if the atmosphere is saturated, why would entrainment have any effect at all on clouds? And so why would you have any CAPE at all? But this equation tells you as the relative humidity goes to 1, that's where you get the biggest CAPE. And the answer is that relative humidity is not an independent variable. It's set by the clouds themselves. And in fact, what happens is you increase the entrainment rate of clouds, two things happen. CAPE goes up and relative humidity goes up. The relative humidity equals 1 limit is actually the limit of infinite entrainment rate. This next term is interesting. It is tantalizingly similar to Carnot efficiency. I don't actually know if there is a connection there, but it's close enough looking to one that we'll just use the letter eta to represent it, in being hopeful, I suppose. And then finally, we look over here, we see QV star of the surface temperature. This fits the lore. We now have a theory, the first closed form theory for CAPE that explains why it is we get Clausius-Clapeyron scaling of CAPE, why we would get those large increases. And that's important because that's what was driving the large increases in lightning in the global climate models. Now, I'll also mention to my colleagues in the audience who are multiplying numbers in their heads right now, that if you take this equation, you're going to get numbers as big as 15,000 joules per kilogram, which is much too high. What I'm omitting here for simplicity is precipitation efficiency. I'm assuming precipitation efficiency is 1. If you include it, this term gets modified, and it brings numbers back down to about 3,000, 4,000 joules per kilogram, which is what you observe. So one of the other benefits of this, so here I'm showing temperature and CAPE on a log axis here, and I'm plotting in the black, the full theory, the dashed, the simplified theory on the previous slide. What's nice about being able to derive things with pencil and paper is you can find out where certain behaviors break down. And you can see through the derivation that this CC scaling, this Clausius-Clapeyron scaling of CAPE should break down at a temperature of around 310 Kelvin, around 100 degrees Fahrenheit. That's information we wouldn't have, of course, if we relied on lore alone. Okay, so we can add this little piece of information to our slide up here. Now, if we're talking about the speed of clouds, we need to know something about the balance of forces. Like CAPE is the total amount of energy available to a storm cloud, but how does it use it? Does it use it in converting it to kinetic energy, which would be going directly to speed, or does it spend some of that energy dissipating against drag, basically, turning it to heat? So that's the kind of question we want to ask. We're going to ask, if we've got a cloud of a certain buoyancy, then what speed does this generate? Basically, I want to ask this question. Are cloud thermals slippery or sticky? And I'll explain what I mean by that. So here are cloud thermals. Here are two cloud thermals. One's rising front and center, and the other is rising to the left and behind it. And if I just stop so you don't get ill watching this choppy video, there they are. Cloud thermals are basically the quanta of moist convection. They are buoyant, turbulent, quasi-spherical vortex rings. And if you spend time watching time-lapse photography of convection, or if you study the output from these cloud-dissolving models, you'll see that convection really comprises repeated risings of these cloud thermal bubbles. So if we want to understand what the speeds in convection, we really need to understand the speeds of these cloud thermals. So these are the objects of study here. Now we can apply a very simple momentum equation to these. Here, W is the vertical velocity. So dW dt is the acceleration of that cloud thermal, and it's equal to the buoyancy minus the drag. And one hypothesis would be the following. Would be that there's a dominant balance between dW dt, the actual acceleration, and the buoyancy. So this would be saying that the acceleration equals the buoyancy, and the drag is small or negligible. An alternate hypothesis would be that cloud thermals quickly achieve their terminal rise speed and achieve a state where the dominant balance in this momentum equation is between buoyancy and drag. Now, the argument for the slippery hypothesis comes from this 2013 paper, which they titled Slippery Thermals. That's the origin of the word slippery here. And their argument goes like the following. They say, well, if we look at the internal circulation of these cloud thermals, it really resembles a Hill's vortex. And a Hill's vortex is this very nice solution to inviscid incompressible flow, where you have this spherical blob of fluid with this vortex ring slipping effortlessly through the fluid. And so, well, the cloud thermals look like that. They must also feel no drag. Now, I'll add a comment here, which is that the reason these Hills vortices feel no drag is because they have this perfect fore-aft symmetry. There's a high pressure region at the front of the Hills vortex, but there's an equal high pressure region right back here on the back side. And that makes there be no net pressure gradient across the Hills vortex, and so no drag force. The alternate argument, the one for sticky, we retorted in 2015 with a paper called Sticky Thermals, is the following. Hills vortex is a beautiful solution to inviscid flow, but the real world is not inviscid, and objects in the real world feel drag. And they feel drag because that symmetry between front and back is broken. And if you look at a cloud thermal, if you just look at that movie I showed just a minute earlier, you'd see quite clearly that that symmetry is broken. These quasi-spherical vortices are rising into clear laminar air, and behind them is a turbulent cloudy wake. So we made the case not just based on that kind of argumentation, but also looking at cloud resolving simulations here and diagnosing the drag forces in a model. But we'd like to go beyond that and actually see if we can make a statement. See if we can measure this in the real world, measure it from observations. So if only we had some way to measure the sizes and speeds of real clouds in the atmosphere. Well, that movie was nice, where we could see the clouds moving. But the problem is we have no sense of depth. I can look at this cloud, and it's a pretty cloud, but I have no idea if it's close to me and only 100 meters wide, or far away from me and 10 kilometers wide. So I can't measure length. And if I can't measure length, I also can't measure speeds. But what if we could use multiple cameras? Most famously used, perhaps, for bullet time in The Matrix, where you set up a whole array of cameras, all firing at almost the same time. And that allows you to get a real sense of depth and perspective. What if we could do that with clouds to get a similar sense of depth and perspective? Actually, we don't need even multiple cameras. We need just two. Two is perfectly sufficient to do that. And the technique is called stereo photogrammetry. It's basically triangulation of cloud features to figure out where their 3D position is. It's a very quantitative technique. And I'm excited that what we've been able to do is take this technology that has been only used a handful of times in the past 60 years because it's so laborious. It uses so many person hours to do. And we've been able to automate it from automated feature identification, matching, and reconstruction to make this a viable meteorological tool. And the majority of the thanks for this goes to Lucia Noctem, who's also sitting in the audience, who's a project scientist here and a computer scientist by training, who's done a really excellent job with this work. So our first camera setup is in Miami, and if you forget where Miami is, it's in Florida. Here, and if we zoom in, you can see our locations of our two cameras. There's one at the Rosenstiel School of Marine and Atmospheric Science here, and then I went there in 2012 to set up our second camera to do stereo at the Mass Academy, a public high school there. It's about a kilometer up the road from the first camera. So here's the Mass Academy. It's a very nice looking school. And they've got this wonderful tower here in the front onto which we could mount our instrument. And there is our instrument. It's a security camera. In fact, it's a security camera that sits directly above it. The only difference is that one is looking at thieves, and ours is looking up at the sky. So that's it. And this gives you a sense of where we're looking. That's Shahid, who helped set up the camera. We're looking out over the ocean, looking at the convection there. And those movies I just showed came from one of these cameras. Since then, we've also set up stereo cameras in Oklahoma as part of the Department of Energy's ARM project. They have a large meteorological site there. So we set up 4 cameras, 2 pairings, again separated by about a kilometer. And the picture that was on the poster was taken by one of those cameras. This is a storm front coming in across the plains here. But what you see most of the time is not that kind of stuff, but more fair weather clouds like this. Now, if you look at a scene like this from a single photograph, there's very little you can say. In fact, I say there's nothing you can say quantitatively, really, about the cloud field. I can't tell by looking at this which cloud is closer to me, which cloud is further away. I can't tell anything about size. I can't tell you which cloud is higher than the other one. But if we use stereophotogrammetry, we can get some information. Stereophotogrammetry can tell us that, oh, here are the clouds that are within 8 kilometers of the two cameras. Okay, that's something. I couldn't have guessed that by looking at this single picture. But of course, we can go far beyond that. We can get quantitative and reconstruct that whole scene. So this shows the location of the clouds out to 8 kilometers using just that photograph and the one other photograph from the other camera. The two cameras' locations are shown here by the red and blue cubes, separated by about 1 kilometer. The cones show their fields of view. The purple are the clouds. And the units on the axis here are kilometers. So with this, you can see that, oh, okay, the cloud base is at 1.5 kilometers. And the highest cloud is from that picture on the right-hand side, the northern side, and its cloud top is 4 kilometers. So we can be terribly quantitative with this technique. And that's exactly what we need. We want to be able to measure width and speeds of clouds so we can say something about the momentum budget. So let's go back to this equation. I'm going to just rearrange this a little bit to write it like this. And let's think about what we can measure. With the stereo cameras, I can measure dW dt. And with the stereo cameras, I can measure the cross-sectional area and the vertical velocity. W again is the vertical velocity. And this is just a standard drag law here. I can measure these pieces. Now what about CD? Well, this is where those two hypotheses come in. We can assume either a slippery hypothesis, which would be no drag coefficient, or drag coefficient equals 0, or a sticky hypothesis where CD equals 1. If we make one of those assumptions, that then gives us buoyancy. Oops, buoyancy, there we go. And that estimate of the buoyancy can then be compared against observations of buoyancy, both from planes flying through clouds, measuring the temperature very carefully, and also from those cloud resolving simulations, which just basically solve the governing equations for the compressible fluid of the atmosphere with water. So let's see what happens when we do that. So we're going to look at a whole large dozens of cloud thermals and generate some statistics here. So I'm going to plot the estimated buoyancy using the stereo data over here. Note that this is a log axis. And over here, there are going to be the different assumptions. If we use a slippery hypothesis, then this is the distribution of cloud buoyancies that we estimate, with a median of 0.1 Kelvin. If we use the sticky hypothesis, where we have drag, then we get a median buoyancy around 0.3 Kelvin. Now, what about observations? When we fly through planes, what we seem to find are values around 0.5 Kelvin. And when you look at large eddy simulations or cloud resolving models, you find cloud buoyancies around 0.3 Kelvin. So you see here that the sticky hypothesis is consistent with the observations and the cloud resolving models, while that slippery hypothesis is not. So are cloud thermals slippery or sticky? From that first paper I mentioned, titled Sticky Thermals, we looked at cloud resolving simulations and we concluded that clouds are sticky, and we came to the same conclusion looking at stereo photogrammetry output. The clouds are sticky. And what that means is that for mature cloud thermals, there is a dominant balance between drag and buoyancy. In fact, you can show that the distance of which the cloud moves to reach that terminal rise speed is quite short. It's comparable to its diameter. So on this diagram, we can add our last piece of insight here. Is there drag on rising clouds? And the answer is yes. The drag roughly balances the buoyancy. They've reached the terminal rise speed. Now, to this question that I was asking at the very beginning, we still don't have an answer. But I feel like we're getting a lot closer. In the past 2 years, we've made a lot of progress. So I'm optimistic that soon we'll have a theory for how the atmosphere works that would include an answer to this very basic question. So thanks.
Questions?
Eugene?
Question? Yes. So a couple questions.
So the question is, what sets the cross-sectional area of the clouds that we're measuring with the stereo cameras? That's question number one. The second question is, what sets the tops? For the cross-sectional areas, a good guess is that it's set by the depth of the boundary layer. The depth of the boundary layer is set by the relative humidity of the surface, which in turn is set by energy constraints. And so you'd imagine that you can launch cloud thermals that have a size that in the horizontal is comparable to the depth in this kind of neutrally stratified fluid. So that might give you a size around 1 kilometer, and indeed that's roughly what you see. It's for the subcloud boundary layer, basically from the surface to where you get saturation, where you get those flat bottoms to the clouds. So that depth is set by a basic energy constraint, and that depth roughly corresponds to the overall width of these clouds in the atmosphere. But if you wanted a more detailed answer than that, we don't have a more detailed answer than that. As to the tops, clouds reach different altitudes depending on, one, their precise width, how susceptible they are to entrainment, how juicy in entropy the boundary layer is that they're being composed out of. And so clouds reach all sorts of variety of heights. At the end, the very top, the tropopause height, that's set by a combination of dwindling emissivity of the atmosphere due to very little water vapor up there, and also increasing ozone levels, so increasing absorption of solar. So basically, clouds will go as high as there is radiative cooling, because if there's any radiative cooling at all, clouds have to get there to do the job of balancing it. So that sets the upper limit.
Yes.
You mentioned that previously the atmosphere after the concentrate to power of 4.9%. When you say that the concentrate area happens from positive change from multiplied by 2, why don't you add some power to change and keep kind of optimized to get a better fit?
One could add exponents to those. Already, since we're explaining 77% of the variance, it already does a pretty good job. And also, I can picture how that fits with an exponent of 1. I can picture how this fits into an energy budget perspective. If I start putting exponents on there, it becomes much more difficult to come up with a kind of justification along those lines.
You and then.
I've understood that the issue of clouds, what they do to the atmosphere and so on, is a big question mark in climate change models and so on. Does this work advance that or help people figure out exactly what they're trying to do in the future?
Yeah, so that's the motivation actually for the existence of my research group and the fine people who work with me. So we're trying to understand how clouds behave so that we could improve our representations of them in climate models. In the current climate models, they report climate sensitivities, that is, increase in global temperature to a doubling of CO2 that still ranges from 1.5 degrees Celsius to 4.5 degrees Celsius. So it's factor of 3 range. And clouds are the largest culprit there. And in fact, interesting tidbit, of all of the knobs and parameters you can touch in a global climate model, the one to which the climate model is most sensitive is the entrainment rate, which is this injection of clear air into clouds, which seems like this esoteric, turbulent process nobody should have to worry about, but it turns out being the most important parameter in terms of climate sensitivity.
Can you tell us anything about where these additional lightning strikes will be? Will they be over deserts where we don't worry about fire, or will they be forested areas?
We don't know yet, but we're working hard on the answer to that question. Alex Charn, who was a co-author on one of those the sticky thermals paper, who was an undergraduate at the time, he's now a graduate student here. He and I are working on that very question.
Anthony Del Genio some years ago postulated that using the Southern Great Plains site like you did, that the lower boundary wasn't much like light. That's for you. But I study the Arctic. So thank you for the great explanation of Cape, because I've really never understood it until now. And I was wondering, so always said that relative humidity is stay constant. And I was looking at your sort of parameterization there and wondering how lightning strikes would be affected, and if you could comment on whether you think that it's actually in fact true.
Yeah, so this is another piece of the meteorological lore, which is that relative humidity stays constant as we warm things. And you ask people why, I say, well, you know, we don't have any theory for why it should change, right? And in fact, the global climate models seem to predict a fairly constant relative humidity. But they actually do something. It's not exactly constant. What happens is, in the tropics, the profile of relative humidity seems to shift upwards. And this theory explains why that happens. It turns out that relative humidity is described by an invariant curve in relative humidity temperature space. And so if you measure 70% relative humidity at a temperature of, say, 270 Kelvin, then you warm the planet, you go back to, you find the new height where 270 Kelvin is, you'll find 70% relative humidity. And this is something that's borne out by this theory and also by these cloud resolving simulations. And explains this behavior, I think, that we see in the global climate models.
And so the lightning rate that you proposed here is going to maintain.
Well, yeah, the global climate models, they incorporate all of the effects that I've included in the theory here. So they presumably, the effects of the small changes in relative humidity are already baked into these numbers.
Okay, Elliot, and then maybe last question will come from over there.
Given that you've explained the equation of motion for the clouds naively, I might think there was another way to say this, that you have no first principles model for what actually sets the buoyancy.
That's exactly right, yes. So we know that the atmosphere is just in the right place to just allow clouds to ascend to the atmosphere with a little bit of buoyancy. And different clouds of different sizes have different buoyancies, but we don't have a theory for what's the spectrum of those buoyancies. The theory that I'm using here is very simple and basically ignores that question. So we could assume that the worst storms are completely non-entraining, but that's not quite right either. So yeah, what sets the actual buoyancies is one of the big puzzles.
Any last question somewhere? Yes.
Is it necessary to think of, we talked about the clouds rising, clouds moving. I don't think very much about clouds doing that. I think to me, and I would think a particular cloud is being used for a strong example of this. The cloud goes into conditions. The cloud, the atmosphere produces a cloud. If the cloud appears to rise, it's because the change in atmospheric conditions causing the appearance of the cloud to move. I find it hard to say the cloud itself is moving, the conditions of clouds are moving.
Yeah, so there are different types of clouds, of course. And I should be careful, and I try to be careful, to say I'm talking about convective clouds here. So the lenticular clouds that you're talking about are caused by there's a layer of high humidity that gets bumped up and saturates and just hangs there. There are things like stratocumulus or fog. They don't have much vertical motion. The clouds I'm thinking about here are things like cumulus, cumulus congestus, cumulonimbus, the things that do have vertical motion through some vertical extent.
Okay, let's thank David one more time.